In today's class, we're going to finish up our discussion of gases by looking at what are called real gases, which deviate from the ideal gas equation, and then also use that to review a few ideas and look at some important applications. Here's an idea that we had in a previous class where we were asked to analyze the image and look at a few different properties like the pressure, the partial pressure, the density. When I'm answering these, for the first question, I could simply look at the number of particles. Same thing with the second, if I was looking at the number of particles of helium to get their partial pressure. Density was a little different. With density, I needed to consider a characteristic of the particles, which was their molar mass. In this case, if they're all at the same temperature, they all have the same average kinetic energy. That consideration of the density, where there was a property of the gas particles themselves, which was their mass, that was important, that's something we're going to extend and look at today. We saw how the rate of effusion also depended on the mass. When it comes to properties of gas molecules, I think we know a lot. We can take a gas molecule and we can consider the type of bonds that are found within it. We consider whether it's a polar molecule or not. All of those ideas are going to be relevant when we consider real gases. The kinetic molecular theory, that was used to explain the ideal gas equation. An important idea was that attractive and repulsive forces were negligible. When would the attractions or repulsions be significant? If the temperature was low or the particles were close together, these were conditions where attractive forces could be relevant. This is saying that the volume of the gas is also important. If the volume of the gas is large relative to the volume the volume of the gas particles is large relative to the overall volume of the container, that was going to lead to deviations from the kinetic molecular theory. That's what's shown within the image right here. So this is giving us a clue that when we're trying to think about characteristics of real gases, ones that deviate from the ideal gas equation, we need to consider aspects like the size they occupy and also the presence of attractive or repulsive forces. A gas is going to be most ideal, consistent with the equation PV equals nRT, when the gas is at a low pressure and a high temperature. It's going to be most real, which means it deviates from that when the pressure is higher and the temperature is low. Under those conditions, attractive forces are going to be relevant. Examination of attractive forces between molecules, that's what Chapter 11 focuses on. If we're thinking about ideal gases and real gases, we've seen how the kinetic energy is a reflection of the temperature. That's what the thermometer is measuring, the average kinetic energy of our particles as they move through space. In a gas, how does this kinetic energy compare to the attractions that we have acting between the different molecules? In this image right here where we see a solid, we have it at a low temperature, only 27 K, for O2 as a solid. And they're all stacked up like this because there are attractions between the molecules. If we were to change the temperature, we could transform it into a liquid. And at an even higher temperature, where the kinetic energy is even greater, it would be a gas. What we find is that the kinetic energy of the particles, when that is greater than the intermolecular attractions, they're no longer being held together. Instead, the molecules can be spread apart like we find in a gas. And if it's an ideal gas, it's consistent with this equation PV equals nRT. What if it's not an ideal gas? What if the characteristics of the gas particles themselves are important? Well, then we need a more complex equation than PV equals nRT. There are different equations that can describe a real gas. One of them is shown there on the right-hand side. That's called the van der Waals equation. I see P, V, nRT in that, but I also see some other terms. This A term and a B term. A and B will be properties for a specific substance. So helium has a specific A value and a specific B value. H2O, specific A value, specific B value. The A values correspond to the attractions that are present between the molecules. or between the particles of a monatomic gas. B is a reflection of their size. How do these result in non-ideal behavior? When there are attractions present, the volume of the gas would be smaller than one would predict using PV equals nRT. Or you could say that the pressure is less. How this occurs at the particle level? Imagine we have a particle that's going to go and strike the wall of the container. In an ideal gas, that would exert a particular force. In a real gas, what if that same particle is also experiencing attractions between other gas particles? Instead of striking the wall of the container with the full force, it's going to be smaller because it's also being attracted back within the container to the other gas particles. This would mean that the force with which it strikes the wall is smaller than you'd anticipate. The size works in the opposite way. The size, it acts like a repulsion. So we could think of that leading to a volume that would be larger than you'd anticipate using PV equals nRT, or the pressure being greater. I took the data for both the A and B values and I made a plot. Let's analyze the data. Stronger attractions are found between what type of gas molecules? Large or small? Well, it looks like we have a pretty good fit there, where the larger particles, those with a larger B value, are experiencing stronger attractions. Now, if we look closely at that, we have one that seems like an outlier. H2O seems different. It is experiencing a stronger attraction than I would have predicted based on its size. What explains this? Why do you think H2O as a substance experiences stronger attractions than its size would suggest? How is it different than the other substances in this list? Looking at the list, H2O is the only polar molecule on the list. So polar molecules seem to be having greater attractions between them than I would otherwise predict. When it comes to intermolecular forces in molecules, it appears that a larger size, larger mass leads to larger attractions and greater intermolecular forces. It also appears that polar molecules are ones that will also experience greater intermolecular forces. These ideas are going to be central to Chapter 11 as we consider the partial charges that the different molecules can have and how that leads to attractions between them. Before we move on to Chapter 11, let's focus more on just the molecule in isolation. Before we see how it's being attracted to its neighbors, let's look at more closely at the molecule itself and the properties it might have. An important property a gas molecule can have is it can be a greenhouse gas. I bet you've heard of this phrase before. I bet you've heard of the greenhouse effect. Can you explain it? What's your initial understanding? How does the greenhouse effect work? This particular FET simulation can be used to get an initial understanding. Within this FET simulation, it has a thermometer. It shows the energy that's going into the planet and also going out from the planet, different types of sunlight or infrared radiation that can be involved, and then also the concentration of different greenhouse gases. Let's start our simulation when we're looking at the greenhouse gases during the Ice Age. Sunlight's being directed towards the planet. I see infrared rising, and I see the thermometer going up. I see the infrared rise. Some of it continues to leave the planet, but other infrared is being directed back towards the planet. And if I look at the energy balance there on the top left, it looks like it's reaching a point where the energy in matches the energy out. The thermometer itself, it's now up to around 280 Kelvin. This is corresponding to the Ice Age. Let's look at the same thing, but more in the present day. This is with greenhouse gases similar to what were found in 2020. We again have sunlight striking the planet. We have infrared rising upward. some of it continuing on, but some of the infrared also redirected towards the planet. If I look at the energy balance, it's once again going to be balanced for what goes coming in, matches what's going out. But if we look at the thermometer, higher value. We have a higher temperature when we had more greenhouse gases in the atmosphere. Let's see if we can try to understand what's going on. So when we're thinking about the radiation that's coming from the sun, we could think about the sun as a black body. As the temperature increases, we saw that it would emit infrared radiation. It would emit visible light. And it would also emit in the ultraviolet. In this spectrum, on the far left, we have the ultraviolet, then we have the visible, and on the right-hand side, the infrared. So if the sun is emitting these different forms of radiation, how do they interact with the gases that are in the Earth's atmosphere? Here's a list of different molecules. Which of these are going to be greenhouse gases? What makes a molecule a greenhouse gas? What does it do? Let's try to answer that question. So to get started, let's apply some ideas that we had in chapters 8 and 9. What I'd like you to do, draw a Lewis structure, and based on VSEPR theory, what would be the molecule's geometry? Would resonance be applicable, and would it be a polar molecule or not? So something like this. If we have carbon monoxide, we would be thinking about that as a linear molecule, triple bond between the carbon and the oxygen. Do something similar now for the other molecules. Here would be a representation for the other ones if we're looking at nitrogen, oxygen, carbon dioxide, methane, water, nitrogen dioxide, and ozone. Resonance would be applicable for nitrogen dioxide and ozone. Instead of having a single and a double bond, I think I have an averaging of those. What we're going to do is we're going to explore and collect some data. We're going to use a PhET sim to see what happens when different electromagnetic radiation interacts with the different molecules. Let's use the simulation to collect some data. Within the simulation, we can have microwave, infrared, visible, or ultraviolet photons. They can be directed at a particular molecule. We can see what happens to the molecule, and the different ones we can test are shown here. So let's get started by using microwaves. What I'd like you to do is record whether there is a response from the molecule when microwaves interact with it. And if you can, try to name what you think that response is. We're starting with carbon monoxide. Okay, it looks like something is happening. Nitrogen? Nope. Oxygen gas? Nope. Carbon dioxide? Methane? Water? Nitrogen dioxide. We can test ozone, but let's save that one. If we looked at the responses, we saw that there was a response when the gas interacted with microwaves for carbon monoxide, water, and nitrogen dioxide. That type of motion, we would say the molecule was rotating. It was spinning around. Let's see what happens when we move down to visible light. Let's see if there's any response when visible light interacts with the molecules. Carbon monoxide, nitrogen, oxygen, carbon dioxide, methane, water, nitrogen dioxide. Okay, I see something now. And again, we'll save ozone. So if we were to record our data, when we had visible light, the only one that responded to it that we had was nitrogen dioxide. Within the sim, it was showing it glow somehow. Let's try to understand what that is. But for now, let's just record that's what happens. Let's move on to the ultraviolet. Same thing. Is there a response? And what happens? Nothing for carbon monoxide. No for nitrogen. No for oxygen. Carbon dioxide. Methane. Water. Nitrogen dioxide. Okay, I saw something. What is this sim trying to show us here? With the ultraviolet, it looks like it was breaking a bond within the molecule, and that only occurred for the nitrogen dioxide. Finally, let's test the infrared. Same thing. Let's use the sim to collect some data. Okay, I'm seeing a response from the carbon monoxide. Nitrogen. Oxygen. Carbon dioxide. Methane. Water. Nitrogen dioxide. So we had quite a few responses when we had infrared radiation. That type of motion corresponds to vibrations. All of the ones that we have listed vibrated except nitrogen gas and oxygen gas. Try to make a prediction. When we test ozone using microwaves, infrared, visible, and ultraviolet, which of these do you think would lead to a response for the ozone molecule? Look for the different patterns that we have. Some of these I bet you can answer. Will an ozone molecule respond to microwaves, infrared? How about visible and ultraviolet? Let's make a prediction before we test in the sim. Okay, let's see if we are right. So we're going to go through and use ozone with all the different forms of electromagnetic radiation listed. We'll start with microwaves. We'll move to infrared. Visible light. Ultraviolet. How did you do on your predictions? Did you predict that the ozone would respond to microwaves and infrared? How about responding to the ultraviolet? What's going on within each of these? What's going on with the microwaves? How does microwave radiation interact with molecules? What kind of molecules and what happens? All of the ones listed for interactions with microwaves were polar molecules. They all have a permanent dipole moment, and they rotated when they interacted with the microwaves. This particle motion, this is how a microwave oven works. If a microwave then interacts with a water molecule, it sets it in motion. Remember, the motion is what we're thinking about when we're considering aspects of the temperature as the molecules move through space. When we have many water molecules, when the microwaves interact with them, they start spinning around, rotating, and then this starts them tumbling and moving about. As they're moving through space, That's what our thermometer measures. This is how a microwave oven heats up your food. How about the infrared? This one's especially important for the greenhouse effect. What types of molecules does the infrared interact with? Molecules are going to vibrate if the molecule's dipole moment changes during the vibration. When you have a diatomic molecule, like N2 or O2, that are the same atoms, turns out those do not respond to infrared radiation because there's no dipole moment present, even if they were to vibrate. In contrast, if you have different types of atoms present, that vibration could lead to a dipole moment, and that means it interacts with the infrared. If we're to look at the particle motion here for carbon dioxide, it is a nonpolar molecule when we have our vector quantities for the bond dipoles being equal and opposite. But when we have this vibration, that's no longer the case. When we have the vibration, it turns it into a molecule with a dipole moment. That's going to occur for all of the ones that we have listed there. They are either polar molecules or they have an induced dipole moment when they vibrate. When we're thinking about ozone, ozone is said to interact with infrared radiation. Turns out there are 3 ways that an ozone molecule can vibrate. What do you think those motions look like? Can you try to act them out? Here are the 3 motions. We could have symmetric vibration, where the bonds are getting longer and shorter, an asymmetric one, and then a scissoring, where they stay the same length, but we see them moving, the atoms on the outside moving closer and farther together. I don't know about you, but the different vibrational motions, I really like these simulations. And that's probably my favorite motion there. The electronic transitions, only one of them responded to visible light, and this would be one that I couldn't predict just by looking at the shape. These are not predicted simply by looking at the molecule. Electronic transitions, we've seen those before, where we're going to an excited state when a photon moves an electron from a lower to a higher energy level. Where are those excited states? Well, they could be present and described using molecular orbital theory. Molecular orbital theory and accompanying calculations could be used to describe whether we have an excited state that matches a transition with a visible light photon. That's something we could calculate, but again, I can't simply look at the molecule and determine if that's going to take place. For the ultraviolet, we saw that we could break bonds. That's an idea that we had back in chapter 5, where we were thinking about bond enthalpy values. Here's bond enthalpy values if we go from carbon monoxide to water. The smallest value I see here is 464 kilojoules per mole. How about the bonds in nitrogen dioxide and ozone? We see listed the data for a nitrogen-oxygen single bond and a nitrogen-oxygen double bond, and the same for the oxygen. What would be the bond enthalpy values for nitrogen dioxide and ozone after we account for resonance being present? I view the bond order in those as being a bond order of 1.5, as we are combining and averaging a single bond and a double bond. So for these, I would say they'd have bond enthalpy values as an average between the single and the double. Notice how these values are smaller than any of the other bond enthalpy values. So we could have ultraviolet radiation break those particular bonds. That phenomenon is especially important for ozone. The ozone layer crucially protects life on our planet by absorbing ultraviolet radiation. We saw that ultraviolet radiation is coming from the sun. What happens is that ultraviolet radiation will lead to bonds being broken within the ozone molecules rather than traveling through to the planet and damaging the cells within organisms like ourselves. So that's what's being shown within this picture here, where we would have ultraviolet being absorbed within the ozone layer as it breaks bonds within those ozone molecules rather than reaching us. And the depletion of the ozone layer, that was a big environmental concern when I was a kid. Does some ultraviolet still come through? Absolutely. That's what would lead to a sunburn. When it comes to greenhouse gases, those are ones that interact with infrared radiation. The concentration and the importance of different greenhouse gases is listed in this figure here. Very important one is carbon dioxide. The concentration of carbon dioxide has dramatically increased in recent years. This shows data over a huge time span. This x-axis is in thousands of years before today. So this is going all the way back 800,000 years, which is incredible. There were cycles in which carbon dioxide was higher or lower, but we are in an entirely new regime as we pass more than 400 parts per million. Dramatically different. Where's it coming from? There's no surprise. As we saw back in chapter 3, every time you have a combustion reaction, you're going to produce carbon dioxide. The combustion of octane absolutely produces carbon dioxide. It's unavoidable. And that's what's leading to this dramatic increase as societies have become industrialized. Now, we have another aspect to our explanation to consider. Why does the Earth get warmer, not colder, when we have more greenhouse gases in the atmosphere? If greenhouse gases act as like a barrier, why don't they block the radiation before it reaches our planet? Why does a greenhouse gas make the temperature go up, not go down? Share some ideas. Do you have a answer for that? What we find is that when light interacts with matter, it's shifted to a lower frequency. That's what's being shown, how light can find its way through the greenhouse gases and then get trapped within it. That's what's being shown within the simulation, how visible light can come in and turn into infrared as it's being emitted. That idea of shifting to lower frequency, we saw that earlier when we were looking at Bohr's model for the hydrogen atom. In this case, ultraviolet radiation, ultraviolet photons are interacting with that electron. It's moving it to a higher energy level, and then when it returned, it didn't have to be ultraviolet. It could be in the infrared, it could be visible. The photons were being shifted to have lower energy. And that's what's taking place in terms of the greenhouse effect. We can have visible light go through the atmosphere, turn into infrared, and have that infrared subsequently get trapped as it interacts with molecules that we saw just a moment ago. Now, this particular then phenomena, the science behind it, it's a lot of general chemistry. Here we have some data to consider whether the people in the different societies, I would say, know that general chemistry. Here we see different countries where we have a highest share of people think that the climate change is indeed due to human activity, and ones where that's being denied. Within our set here, the U.S. is unfortunately right near the top for folks that do not think climate change is occurring. Now, one thing I would say within the data, I don't love that term believe. As our t-shirt tells us, science, it works whether you believe it or not. It's not about having a belief in climate change. It's having an understanding of the phenomena like we've just been discussing. Now, the idea that we have climate change deniers, over your lifetime, has begun to change. It hasn't begun to change, however, one would say symmetrically across the population. It's gone up quite a bit for folks that are Democrat or lean Democrat, and for Republicans, not very much change. It's really unfortunate that the scientific issue has become a political one. When I say it's become a political issue, here I have different quotes. These are all discussing aspects of climate change and climate science. What I'd like you to do here, two-part. First of all, which of these quotes do you agree with? And then second, try to match up the quote to these politicians. One is from Donald Trump, one is from Joe Biden, one is from John Kerry, and one is from Mitt Romney. Discuss which ones you agree with, and then try to match them up. Here's the different politicians involved: Biden, Kerry, Romney, and Trump. As we are thinking about the implications for this, policy issues and policy choices pertaining to climate change are absolutely part of our everyday lives. It's really different, I think, than the science itself. Again, it's not about believing in climate change, it's about knowing the science. If you'd like to learn more, there's this really cool certificate program for undergraduates involving climate change. This is out of the Earth Sciences Department. Different coursework is listed here. I'm putting together a course myself looking at aspects of climate change and what we can do to make a difference. So it's also going to be part of the certificate program in the future. If you're interested in learning more, I definitely think this would be a good spot for you to look.